Hello everyone. Today we are going to analyze this beam using flexibility matrix method. Before analyzing, let's see the beam on time. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, there is an UDL 12 kN per meter acting for the full span. In the span BC, there is a point load 25 kN acting at 2 meter from the point B. In the span CD, there is a point load 16 kN acting in the center. In this beam, there are 4 hinged supports in the point A, in the point B, in the point C, and in the point D. There are hinged supports. Span AB is 4 meter long, span BC is 5 meter long, span CD is 3 meter long. In this analysis, the number of unknown reactions and moments are 4. They are RA, RB, RC, and RD. The available equilibrium equations are 2. Sigma m is equal to 0 and sigma v is equal to 0. The degree of static indeterminacy is equal to 4 minus 2. 4 minus 2, we will get 2. Let us release MB and MC. When we release the moments from the point B and from the point C, this beam becomes 3 different simply supported beams. These beams are called the released structure. We have made the released structure. Now let us make the coordinates diagram. In this analysis, we are having two coordinates. In the points B and C, we are having the coordinates because in these points only we have removed the moments. Now let's see the formula to calculate the final moments. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix, where P matrix is the final moments or forces, delta matrix is the flexibility matrix, delta matrix is the final displacements, delta L matrix is the displacement in the coordinate direction. Inside the P matrix, we will have MB and MC because these are the moments we have removed. In the P matrix, delta L matrix and delta matrix, we will have two values because in this analysis we are having two coordinates. In this formula, first let us calculate delta L matrix. To make the delta L matrix, we have to form the conjugate beams using the loads. First, in the beam AB, let us make the conjugate beam. Here, UDL 12 kN per meter is acting for the full span. If in the simply supported beam, UDL is acting for the full span, the formula to calculate the maximum bending moment is WL square upon 8. Here W is 12, L is 4. When we apply inside the formula, we are getting 24. Now let us take the beam BC. A point load 25 kN is acting. It is not acting on the center. The formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 2, B is 3, L is 5. When we apply all the values in the formula, we are getting 30. Now let us take the beam CD. Here a point load is acting on the center. If the point load is acting on the center, the formula for bending moment is WL upon 4. Here W is 16, L is 3. When we apply inside the formula, we are getting 12. Using these values, we can make the diagrams. For the UDL, the diagram will be in the parabolic shape. For the point loads, the diagram will be in a triangular shape. In the conjugate beams, we have to divide the moment values by EI. Here we are having three conjugate beams. A dash B dash, B dash C dash and C dash D dash. In these conjugate beams, we have to calculate delta L matrix. Here we have to find delta 1L and delta 2L. Delta 1L should be calculated from the first coordinate. The first coordinate is in the point B. Delta 1L is the slope in the point B. We know that in the conjugate beam, the slope values are the shear forces. So, to calculate the slope at B, we have to find the shear force in the point B dash from the beam A dash B dash and from the beam B dash C dash. For this beam, the shear force in the point B dash is the reaction RB dash. For this beam also, the shear force in the point B dash is the reaction RB dash. So we have to calculate the reaction RB dash in the beam A dash B dash and the beam B dash C dash. First, let us calculate in this beam. This is a symmetrical diagram. So we can easily calculate the reactions. The reactions RA dash and RB dash will be equal to the area divided by 2. The area formula for this parabola is 2 upon 3 into breadth into height. Here the breadth is 4 meter, height is 24 upon EI. When we apply in the formula, we are getting RB dash 32 upon EI. Now let us calculate RB dash in the beam B dash C dash. This diagram is not symmetrical, so we have to take moment to find out RB dash. To calculate RB dash, I am going to take moment about C dash. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. RB dash is acting towards the point C dash in the clockwise direction. So it will be positive and the distance is 5 meter. So 5 RB dash. This UVL is acting towards the point C dash in the anticlockwise direction. So it will be negative. For the UVL, we have to multiply the area with the centroid. The area formula for a triangle is half into breadth into height. Here the breadth is 5 and height is 30 upon EI. So for the area we are having half into 5 into 30 upon EI. Then we have to calculate the centroid. Since we are calculating the movement towards the right hand side, we have to calculate the centroid distance towards the right. In this kind of triangle, the centroid distance towards the right is L plus B upon 3. Here L is 5, B is 3. So for the centroid, we are having 5 plus 3 upon 3. After the calculations, we are getting RB dash, which is equal to 40 upon EI. For delta 1L, we have to add both of the RB dash values. After adding, we are getting 72 upon EI. Now let us calculate delta 2L. Delta 2L should be calculated from the second coordinate, which is in the point C. So in the point C dash, we have to calculate RC dash. We have to calculate RC dash from the beams B dash C dash and C dash D dash. First, let us calculate from the beam B dash C dash. Here RC dash can be easily calculated by taking the total load. Here the total load is area. We already know the area formula of into breadth into height. From the total load, we can subtract RB dash, which we got in the previous step. After subtracting, we are getting RC dash, which is equal to 35 upon EI. Now let us calculate RC dash in the beam C dash D dash. This is a symmetrical diagram. So we can easily calculate RC dash by dividing the total load by 2. Here the total load is the area of into breadth into height. The total load divided by 2, we will get RC dash, which is equal to 9 upon EI. Let us add these two values. After adding, we are getting delta 2L, which is equal to 44 upon EI. In the delta L matrix, we have calculated both of the values. 1 upon EI is constant. Let us take it outside. Alternatively, using the formulas, we can easily calculate the reactions and form the matrix. In this diagram, we have to calculate RB dash. The formula is WL upon 3. Here, W is 24 upon EI, L is 4. When we apply in the formula, we are getting 32 upon EI. Then, in this beam, we have to calculate RB dash. The formula is W upon 6 into L plus B. Here W is 30 upon EI, L is 5, B is 3. When we apply inside the formula, we are getting 40 upon EI. After adding these two values, we are getting delta 1L, which is equal to 72 upon EI. Now let us calculate RC dash in this beam. The formula is W upon 6 into L plus A. Here W is 30 upon EI, L is 5, A is 2. When we apply the values inside the formula, we are getting 35 upon EI. Now let us calculate RC dash in this beam. The formula is WL upon 4. Here W is 12 upon EI, L is 3. When we apply the values in the formula, we are getting 9 upon EI. Let us add both of these values. After adding, we are getting 44 upon EI. So, using the formulas, we can easily calculate delta L matrix. In this formula, we have calculated delta L matrix. Now, let us find the delta matrix. If in the beam there is overhanging, we have to calculate the delta matrix. Otherwise, we can simply enter 0. In the given beam also, there is no overhanging, so we are simply entering 0, 0. Same like delta L matrix, the size of the delta matrix will be according to the coordinates. In this analysis, we are having two coordinates. So inside the delta matrix, we have two values, but both of them are 0 because there is no overhanging in the given beam. In this formula, we have calculated delta L matrix and delta matrix. Only one is remaining, that is the flexibility matrix. Now let's see the size of the flexibility matrix. For 3 coordinates, it is 3 by 3. For 2 coordinates, it is 2 by 2. For 1 coordinate, it is 1 by 1. In this analysis, we are having 2 coordinates. For 2 coordinates, the size will be 2 by 2. Inside the matrix, we will have 2 rows and 2 columns. Now, let us calculate the first row in the flexibility matrix. For that, we have to apply unit moment in the first coordinate. When we apply the unit moment in the first coordinate, here the moment will be 1 and here it will be 0. In the beam B dash C dash also, here it will be 1 and here it will be 0. Using that, we can make the diagram. We know that in the conjugate beam, we have to divide the moment by EI. Here the moment is 1, so we are dividing it by EI. Now let us calculate delta 11, that is the slope at B. To calculate the slope at B, we have to find RB dash. First, let us calculate RB dash in the beam A dash B dash. For that, I am going to take moment about A dash. In this case, I am moving left hand side. Clockwise will be negative, anti-clockwise will be positive. RB dash is acting towards the point A dash in the anti-clockwise direction. So it will be positive and the distance is 4 meter. So 4 RB dash. This UVL is acting towards the point A dash in the clockwise direction. So it will be negative. For the UVL, we have to multiply the area with the centroid distance. We know that it is a triangle. For the triangle, area formula is half into breadth into height. Here the breadth is 4, height is 1 upon EI. So for the area, we are having half into 4 into 1 upon EI. Then we have to calculate the centroid. We are taking moment about the left hand side. So we have to calculate the centroid distance towards the left. In this kind of triangle, the centroid towards this point is 2b upon 3 and towards this side is b upon 3. Now we are calculating the centroid towards this point. So the formula is 2b upon 3. Here the breadth is 4 meter. So for the centroid we are getting 2 upon 3 into 4. Finally we are getting RB dash is equal to 4 upon 3 EI. Now let us calculate RB dash in the beam B dash C dash. Here I am going to take moment about C dash. In this case I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RB dash is acting towards the point C dash in the clockwise direction, so it will be positive and the distance is 5 meter, so 5 RB dash. The UVL is acting towards the point C dash in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid. For the area, we are having half into 5 into 1 upon EI. For the centroid, we are having 2 upon 3 into 5. Finally, we are getting RB dash. For delta 1, 1, we have to add both of the RB dash values. After adding, we are getting 3 upon EI. Now, let us calculate delta 1, 2. For that, we have to find RC dash. No need to calculate RC dash in the beam C dash D dash because there is no load. Only we have to calculate RC dash in the beam B dash C dash. We can easily calculate RC dash by taking the total load. Here the total load is the area half into 5 into 1 upon EI. The total load minus RB dash which we calculated in the previous step. We will get RC dash which is equal to 5 upon 6 EI. Let us apply this value for delta 1, 2. Now in the flexibility matrix, let us calculate the second row. For that we have to apply the unit movement in the second coordinate. When we apply unit movement in the second coordinate, here the movement will be 1 and here it will be 1. Here it will be 0 and here it will be 0. Using that we can make these diagrams. We know that in the conjugate beam we have to divide the moment by EI. Now let us calculate delta 21. For that we have to find RB dash. No need to calculate RB dash in the beam A dash B dash because there is no load. Only we have to calculate RB dash in the beam B dash C dash. To calculate RB dash, I am going to take moment about C dash. RB dash is acting towards the point C dash in the clockwise direction, so it will be positive and the distance is 5 meter, so 5 RB dash. The UVL is acting towards the point C dash in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. The area is half into 5 into 1 upon EI. In this triangle, the centroid distance towards the right is b upon 3. Here the breadth is 5 meter, so 1 upon 3 into 5. Finally for RB dash, we are getting 5 upon 6 EI. For delta 21, let us apply RB dash value. Now let us calculate delta 22. For that we have to find RC dash. First let us find RC dash in the beam B dash C dash. We can easily calculate this RC dash by taking the total load. In this UVL, the total load is the area of into breadth into height. The total load minus RB dash, which we calculated in the previous step, we will get RC dash. Now let us calculate RC dash in the beam C dash D dash. For that, I am going to take moment about D dash. RC dash is acting towards the point D dash in the clockwise direction and the distance is 3 meter. So 3 RC dash. The UVL is acting in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. The area is half into 3 into 1 upon EI. The centroid distance is 2 upon 3 into 3. Finally, for RC dash, we are getting 1 upon EI. For delta 22, we have to add these two values. After adding, we are getting 8 upon 3 EI. In the delta matrix, we have calculated both of the rows. Let us apply the values. 1 upon EI is constant, so let us take it outside. We know that it is a little difficult to find out the delta matrix because we have to take moments on both the sides. If you think that it is very difficult, we can apply the formulas for the reactions and make the flexibility matrix very easily. First, let us calculate the first row in the flexibility matrix. Using the formula, let us calculate RB dash in the beam A dash B dash. The formula is WL upon 3. Here W is 1 upon EI, L is 4. When we apply inside the formula, we are getting 4 upon 3 EI. Now, using the formula, let us calculate RB dash in the beam B dash C dash. The formula is WL upon 3. Here W is 1 upon EI, L is 5 meter. When we apply inside the formula, we are getting 5 upon 3 EI. Now let us calculate RC dash in the beam B dash C dash. The formula is WL upon 6. Here W is 1 upon EI, L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. For delta 11, we have to add these two values. After adding, we are getting 3 upon EI. For delta 12, we have to apply RC dash, which is equal to 5 upon 6 EI. In the flexibility matrix, now using the formula, let us calculate the second row. First, in the beam B dash C dash, let us calculate RB dash. The formula is WL upon 6. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. Now let us calculate RC dash in the beam B dash C dash. The formula is WL upon 3. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 3 EI. Now in the beam C dash D dash, let us calculate RC dash. The formula is WL upon 3. Here W is 1 upon EI and L is 3. When we apply inside the formula, we are getting 1 upon EI. For delta 21, we have to apply RB dash. For delta 22, we have to add these two values. After adding, we are getting 8 upon 3 EI. So, using the formulas, we can easily calculate the flexibility matrix. In this formula, we have calculated everything. 1 upon EI inverse is equal to EI. Then let us add these two matrices. After adding, we are getting this. Then we can eliminate this EI and this EI. For this matrix, we have to calculate the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to calculate inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting the final moments MB and MC. So in this analysis, we have calculated the final moments. Now we are going to calculate the reactions. For calculating the reactions, we have to separate the beam as per the spans. Here we are having three spans AB, BC and CD. So we have separated the beam into three parts. In the span AB, MB will be acting in the clockwise direction. In the span BC, MB will be acting in the anticlockwise direction. In the span BC, MC will be acting in the clockwise direction. In the span CD, MC will be acting in the clockwise direction. Now, let us take the span AB and calculate the reactions. In the span AB, there is only one moment MB which is acting in the clockwise direction. In the span AB, first I am going to calculate RA. For that I am going to take moment about B. In this case I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 4 meter, so 4 RA. The UDL 12 kN per meter is acting towards the point B in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and distance upon 2. Here the distance is 4 meter, so 4 into 4 upon 2. Then we have a moment 21.26. It is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 18.68 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RB1. In the span AB, there are two upward forces, RA and RB1. Since they are acting upwards, both of them will be positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. We have already calculated RA. Let us apply the value. Finally, we are getting RB1 is equal to 29.32 kN. Now, let us take the span BC and calculate the reactions. In the span BC, there are two moments, MB which is acting in the anticlockwise direction and MC which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive, and the distance is 5 meter, so 5 RB2. The point load 25 kN is acting towards the point C in the anticlockwise direction, so it will be negative, and the distance is 3 meter. Then we are having two moments. 21.26 is acting in the anticlockwise direction, so it will be negative. 9.85 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2, which is equal to 17.28 kN. Using the rule, summation of vertical forces is equal to 0, we can calculate RC1. Now, let us take the span CD and find out the reactions. In the span CD, there is only one moment, MC, which is acting in the anticlockwise direction. By taking moment about D, we can calculate RC2, which is equal to 11.28 kN. Then, applying the rule, summation of vertical forces is equal to 0, we can calculate RD. In the point B, we have calculated RB 2 times. Let us add both of them. After adding, we are getting 46.6 kN. In the point C also, we have calculated RC 2 times. Let us add both of them. Finally, we are getting RC is equal to 19 kilonewton. Now we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. Here you can see the shear force values calculations. Using the values, we can draw the shear force diagram. Now we are going to draw the bending moment diagram. For making the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of these diagrams to get the bending moment diagram. To make the free moment diagram, we have to assume every span as a separate simply supported beam and calculate the moments. In this analysis, we have already calculated the ordinates. Using them, we can draw the diagram. Using the end moments, we can make the end moment diagram. To get the bending moment diagram, we have to combine the free moment diagram and end moment diagram. Then, wherever they are alone, we have to mark. Here, the free moment diagram. Here, end moment diagram. Free moment diagram. End moment diagram. Finally, the free moment diagram. Wherever they are acting together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.